Excellent. Well, thank you again, and hopefully we have a great day together. And it's great to see all the black rectangles on the screen, virtual, right? But we make the best of it, and the good thing is like we're all sharing and learning together. So with that, I'll talk a little bit about what we did here in the Americas region. I'm Matt Robinson. I'm going to kind of talk a little bit more at the program level, and I'll kick it over to Levi. It's been a very extended intro, so but then for those of you who are sort of new to ROS Industrial, this event is sort of sometimes an intro to ROS Industrial. What is ROS Industrial? So I touch a little bit on that and some of the objectives, and then kind of some summary of activities, and I'll kick it over to Levi. We've gone over this story quite a few times. The traditional paradigm of an army of robots attacking a lot of the same thing. But in a lot of cases, a lot of interest either working on large things or using custom robots, and it's been challenging historically. Around 11 years ago, ROS came to the fore, and it's enabled and open source more broadly, right? So we think about tools like OpenCV and some of the products that have been built out on OpenCV, the meaning of what we can see around new capability. I think one thing is when we look at industrial robot sales, it's been exciting to see, as we rolled in the 19 data, I think we can actually say now, hey, there are robots emerging in other categories, and that's probably attributable to ROS enabling advanced capability development. Whether or not the end products actually have ROS under the hood, don't know, but there's no doubt with the ROS prevalence in the universities and getting into startups, that new capability at least can be partly contributed to the emergence of ROS. The other thing we see is this real big boom as far as percent sales and handling robots. Now, some of this is also attributed to AMRs as well, because they fall in this bucket as well. And of course, collaborative robots largely getting into initially handling applications, but the advances in machine vision, tools to facilitate navigation, all have their kind of a significant shout out to things going on in the open source community as well, to enable a bigger tent to develop and brainstorm and push advances. So that's a really great trend. It shows that the work we're doing here and providing functional tools just foster innovation, and that's a great story to be part of. What is ROS Industrial specifically? Just to kind of hammer home the point, it's just extending ROS and now ROS2 to industrial hardware, the cameras, the manipulators, and not necessarily specifically hardware, but bridges for traditional industrial protocols, and to industrial applications, as well as providing very industrial-centric utilities such as calibration. That is the spirit of the ROS Industrial Open Source project, right? Just extending ROS into the industrial domain. So it does not displace ROS, it is not different than ROS, but yet extends and provides functions and utilities to extend ROS Industrial to play in the industrial space in all these different realms. As far as our history, right, so here at Southwest Research Institute, there was adoption of ROS largely in unmanned ground systems. Sean Edwards and Paul Voss, and Sean Edwards is the one in working with Yaskawa Motoman, created the first industrial robot actuated by ROS, and then had some kickoff initial projects demonstrating some of the functionality. Formally, the ROS Industrial repo was opened up and started in 2012. And from 13 to 16, the establishment of the consortia, which I kind of talked about how we work together. And so that's sort of the long arch, if you will, of the program's history. This is actually a recently updated map, right? So we talk a little bit about some of the membership, right? So the key is that the consortium serves as this ecosystem, right? And the cool thing is absolutely, right? We have a great array of different type of members and constituents that have different needs and use cases, right? So, just to pick on a couple folks, right? Having a Lincoln Electric Automation, for instance, they're trying to deploy novel solutions to end users, right? So their interests and needs might be different than, say, a 3M, whereas, like, say, a CAT may need the solutions, not necessarily deploy them themselves, right? So all of them have different interests, different domains. So NOV is in the oil and gas business, right? So what their end use cases are drastically different than, say, BMW, right? So this has been a really great sounding board to provide feedback and insight on like what we should be working on. And what are we kind of working on, right? So this has sort of been the kind of go-to distilled version of what our objectives are. It really has boiled down in the recent years into these 4 pillars, right? Make it easier to use, and I'm going to touch on that. We're going to hear a little bit more about that over the next couple days. Advanced capability, right? Got to make a good YouTube video. Well, in the end, right, we want to do novel, new things on factory floors. I joke about the YouTube videos, but in the end, it has to manifest itself, make an iron, so to speak. Interoperability has been really emerging. I think if we would have asked kind of like, hey, what do we want to be doing with open source and this ROS thing like 8 years ago or 7 years ago, I don't know necessarily we firstly would have like thrown up interoperability as a key element. But one thing that came out of both the grants from NIST on MT Connect to ROS and recent work out of the ARM Institute on OPC-UA DDS bridge, it's really highlighted that like, hey, there is some real powerful things we can do here in enabling more efficient interoperability. And someone in the background. And of course, obviously, human-robot interaction. And we tend to think about like the robot handing the worker the tool or helping them lift something, but this has gotten way bigger, right? So we talk about the recent emergence or real tangible, and we're gonna hear a lot over these next couple of days about augmented reality specifically, but this is another real rich area in a number of different ways we facilitate it. As some of you may have heard, and we've talked about this, Levi's helped come up with this sort of strategy here initially, and a number of folks have sort of been making contributions in this space. But this idea about that, hey, as ROS2 becomes more and more prevalent, we really are making the effort to build ROS1, ROS2 independent. So all of the core key kind of, if you will, details down inside that make the magic happen. The intent is that this is sort of either pure CMake or C++ libraries, and then of course we wrap in the appropriate ROS distribution. There's a number of benefits to this, right? It makes us able to support end users who are still interested in taking advantage of ROS1 in the long history, or there are systems running in production that are ROS1. There's no really reason to change. If it's just running, just let it run. But if there are, say, advances that are interested to be taken advantage of, what can we do to facilitate that, as well as continue to move the ball forward and provide those who are wanting to blaze trails with ROS2 access to some of the latest and greatest developments. And so that's been really a motivation driver, right? And that's kind of what that bullet says. So what about ROS2? What are we doing to try to further ROS2, right? So one thing that happened this year is obviously a lot of work on the training. I wish my slide was kind of obscured, but that's fine. The big thing we did is we rolled out more formally proper ROS2 industrial training. Now, there were some bumps along the way. We provide or send out a survey every time we do ROS industrial training, and we're trying to actually effectively action that feedback. We know there's some gaps about what is fully available, right? So it brings up like, oh, we got to pop back in ROS1, do this little bit, pop back to ROS2. But in the end, you can still deliver, and we'll have examples over these next couple of days about projects being done in ROS2. There's always some bumps in the road, but that continued learning and like, hey, let's solve some of these challenges, move the ball forward, right? So in the end, we've put out some ROS2 training. There's been some hiccups along the way. We have talked about, in certain cases, porting practices, how to use the bridge. Our full-fledged basic training went full ROS2 in February 2021, and we've been doing it since, trying to continuously update it as things become more fleshed out. Also in parallel with this, we did our first virtual training. We had requests in the past about virtual training, so we've been running on Zoom, combined with Zoom and Slack more recently. At one time, I believe we used IRC. And of course, we leveraged the AWS EC2 instance. For those of you who have been through training in years past, you may remember we provided a pre-configured virtual machine. We are still attempting to maintain the virtual machines because they do offer a sense of utility. Unfortunately, when training is over, we leave the EC2 instances up for a while, but at some point we turn them off, right? Because they're kind of, when they're on and we leave them available, I mean, we pay for it. So we do keep the virtual machines available for students to be able to pull down. and leverage, like say, take home, something they can continue to work with after the training is over. So that's been a benefit. Not everyone can use virtual machines with the state of kind of modern IT security concerns. This AWS EC2 instance has been a nice tool and something we're going to probably continue to use in the future as we consider face-to-face training again. We will have, for those members who will be making the workshop tomorrow, we will have a breakout session on training. So I would love to hear about face-to-face, virtual. Obviously in face-to-face, the labs were hugely valuable. Everyone liked making robots move. What do we do for labs in the virtual sense? We've run into some roadblocks with what reasonably we can do and still be safe. That may evolve as obviously people come back to the lab. We can even do virtual trainings from here or run mixed. Maybe when there's actually people monitoring it, the e-stop on the button if someone's remote controlling it. Those are all questions we need to answer. We've been doing a lot of collaboration. I like to highlight the fact that members work together, right? So that's the biggest kind of really cool thing. Even back in my time at Caterpillar, my favorite part was working with the other members and learning what others were doing. And that's no different, right? So Picnic, I linked to the blog they wrote, and you're going to hear from Andy from Picnic later about their journey on the ROS2 driver for UR. And of course, we'll hear later about MathWorks and Delph working together. And of course, ROS-I members working with our partner or Consortia, the ARM Institute. There's a number of examples, and you'll hear more about those throughout the week. This is the specific example. The real neat thing about this particular project I highlight is that we put a full ROS2 example application out there you can introspect and poke at. Like, what does that look like, including the bridge? And so the GitHub link is there. I won't belabor this. Spirit Aerosystems is going to be discussing this development, so look forward to their talk today, actually. One of the things that came out was a lot of interesting things on training. I will be talking a bit more about this in the member update tomorrow. But one thing is we're really interested in these other training for these other roles in the organization, not just developers. So stay tuned as we think about that. With that, I'm going to hand it over to Levi. Levi, I can index for you if you want. The floor is yours.
All right. Can everybody hear me okay?
Sound good.
All right. So I'm going to give some updates, some internal research and development and both things, part of the ARM Institute, that projects we've been working on over the past year. Those involve improvements to collision checking, implementing a parallel process planning pipeline. I'll show an example application, also technology around kinematic calibration, giving an overview of our offline Toolpath planner and updates related to that, and the adaptive force control that was part of the Spirit ARM project. Next slide. So I guess over the past year, we've been trying to improve some of our core capabilities to get to the point where we can do more real-time motion planning or just-in-time motion planning that we'll be showing a demo on demo day. But what we did is we have currently 3 or 4 different motion collision checkers, and we went through and we benchmarked those. We found the bottlenecks, and we did a lot of improvements, both to our bullet and SCL implementation. Over this period, and on the left, that bar is the number of collision checks able to perform per second. Contact only, penetration, and distance. So those mean contact only means we just care about if 2 things are in contact. We don't want to do distance calculations. Penetration is in reference to things are in collision, so we want to calculate how far in collision, the penetration distance. And then the distance is typically the most computationally intensive, is whether you're in collision or not, I want to know the distance between shapes in my environment. So as part of this, we were able to improve bullet 3 to 5 times. The major improvements we were able to make is to our SCL implementation. We were able to get 25 to 1000x improvements over these 3 different types of collision checking. The 1000x was in the distance calculation piece. Also, as part of this, we implemented a new collision checker that has both CPU and GPU support. And as you can see on the distance, the CPU GPU implementation provided about a 2x improvement, and that's the CPU. I haven't rerun the GPU data, but the GPU is quite a bit faster for both distance and all the aspects. So next slide. The other piece of this is typically a lot of the problems we deal with are around the scan and plan type application, where you have a lot of different rasters, transitions between rasters and to and from home. So we wanted to build out a parallelized application to handle these type of problems. So what we ended up doing is we settled on an open source project called TaskFlow that allows you to build out all of these different tasks, build out computational graphs, and it will handle spinning up and bringing down nodes. It also supports GPU if you have a GPU-based task. So we built a whole framework on top of this for doing motion planning. So you have the ability to build out your pipeline, say, for a raster, which in this case, it'll try traj-op. Say if traj-op failed, it maybe run Descartes or something else, then it runs it through continuous collision checking and then time parameterization. For transitions, with typically free space, you may start out with OMPL traj-op, and you can kind of build out this pipeline, what happens when things fail versus when things succeed. And then you can build out the higher level graph, which is on the top left. This is an example where we do some type of global plan, we do some post-processing, and then every row you see there is running in parallel. So then it would spin off raster 1, raster 2. Those would run in parallel. And then once those finish, it will automatically spin up the other tasks from start, transition, and to end. And we'll show an example on the next slide. So here was an example that we took. We did it both single-threaded and then running through the multi-threaded task planner. So we have a 6-DOF manipulator with a 3-DOF positioner. It makes an example, fuselage, cell, or skin. And you can see the generated process trajectory. It has 7 rasters, 6 transitions, and then 2 free space. It has a total of 380 instructions. Basically, those are Cartesian poses telling it to move L, move free. Single threaded, it took about 7.28 seconds. With a seed, initial seed, it was about 6.8. Then running it through the task-based planner that understands the process and was able to spin things off in parallel, like the different rasters. We were able to cut the time in half. We were able to now plan these type of problems at about 3.2 seconds, and then with a seed about 2.3. So you can imagine the more hardware you have and the larger the problem, the planning time gets even faster. Another internal project that we did was looking at kinematic calibration. So we had a situation where we were taking multiple snapshots and we were trying to leverage the kinematics of the robot to stitch the data together. But it turns out we were getting misalignment, which was affecting the process. So we spun off trying different approaches, looking at both just calibration based on DH parameters and then doing full kinematic calibration. That work is part of the Robot Cal tools that is open source. The point of contact on that is Michael Rittberger. And as part of that, we were able to significantly improve the stitching of the data by having a more accurate kinematic model of our system. We used both Vicon and a PhotoNeo. The Vicon was for baseline for that system. Next piece is we have an offline Toolpath planner that allows you to bring in meshes. You can configure parameters and it will generate Toolpath on the surface, and it provides you the ability to export this. Some new features that have been integrated into this process is we had an internal research project to look at leveraging an open source technology, leveraging the heat method for generating these toolpaths. The one thing that we liked about that technology is it's pretty robust for the data. So it supported both meshes, and it has the ability to support point clouds or octomaps. So right now that is integrated into this offline planner. It currently supports meshes, but we have an internal effort that is updating it to support point clouds. So you don't have to have a mesh. You can get point cloud data and you're able to generate toolpaths. Also has the ability to draw toolpaths on it. And that's open sourced. The other piece is related to adaptive force control. So this was part of the project you saw that Matt presented on, that they were drawing circles on it and generating toolpaths in those regions. We did an internal research to explore a robot agnostic method for adaptive force control, taking feedback through an ATI sensor. Those are both the two repositories on the left, the collaborative robotic sanding that is open sourced, and the work was done leveraging the Cartesian controller with ROS control. And Tyler Marr was the point of contact on that.